coming through, fracturing the crust, melting the crust, and releasing the helium. So I'm not going to go into all this. It's very technical. I don't want to read all of it. But there's a few notes that the magmas, particularly what you see, like Shiprock, for example. This is a good example. It is known as a mafic magma, which is it's like a basalt, okay? And these are also really important for the release of helium because basaltic magmas are low viscosity, which means that gas within the magma is separated. It separates out of the magma, and then it moves as a separate gas phase. The other is basaltic magmas are extremely hot. They're 1,200 to 1,400 degrees Celsius, moving up very rapidly through the crust. Remember I said I only need 180 degrees, and I start releasing helium out of this piece of granite. So this is 10 times almost the amount of heat that is moving up through it. And that's what was happening when Shiprock got in place, or other of these diatremes in our area got in place. The rising magma also fractures the rock because it opens up existing cracks and creates new ones for the helium now to migrate out of. So here's Shiprock, just great. And you can see, what's great from the aerial photo, you can see all the fractures, see all the dikes. You've seen the big walls, right? Those are the dikes. Well, the cracks, those dikes were first, the gases created the cracks first, and then the magma came in afterward and created what you see are the big lava walls. And so those gases were full of helium that was moving. So most of the helium went to the atmosphere. It's gone, it's in outer space now, but some of it got trapped in geologic structures. So this kind of brings it all together. What I just talked about, how you have an intrusive event coming up. It is opening up fractures. It is releasing the helium. The helium then, if it either gets out to the surface or if it finds a geologic trap, some kind of a trap in the subsurface, it will get trapped there. So now we're going to talk about, okay, now we kind of went through real quickly how helium forms, why, where it is. So now we're going to look for, how do we find it? Okay, so helium, looking for helium is a little different than oil and gas. When I just showed you the mechanism for oil and gas, for helium is very different than for oil and gas because my source rock is crust, is basement rock. So it's important. I need to find out where are the cracks. Where were the cracks formed? Where were these intrusive, these volcanic bodies or magma bodies? Where are they in the earth? Okay? So one of the main methods to see inside the earth or see in volcanic or magma bodies in the earth is called aeromagnetic, because like granites and other magma bodies are magnetic. Rocks like sandstone, shales, things like that, they're not magnetic. So when I run aeromagnetic, they're invisible to it. I don't see it. All I see is the basement, which is my source rock, and I see the volcanic bodies in the earth. So that's why aeromagnetic is very important. And what I'm going to show you are some pictures some images of, we flew a very detailed survey. And this is the plane we flew it. You see this little thing hanging? I don't have a pointer, I don't think, on this thing. Maybe I do. Oh, yeah, I do. See right here? That's called a stinger. And that stinger is a magnetometer. It's basically measuring the Earth's magnetic field. And we flew over the survey over the Navajo Nation every quarter of a mile east-west and every mile north-south, and create a grid so that we can create an image of what the magnetic image of the Earth or what the basement looks like under this portion of the Navajo Nation. And this is where we did it, right up here. We did this area, covered about 1.7 million acres, where we did the very detailed aeromagnetic study. And then here's a picture. This is a structure. Here's a structure of what the basement or the granite surface looks like in the subsurface. The red areas are shallow. The blue areas are where it's deep. This is the Defiance uplift, so the Chusca Mountains and all that. That's a very high area. The granites are very high there. And the red dots are where helium has been found. Helium wells that have tested high amounts of helium in this area. And of those, and also the other point is these black lines, you see, it might be a little hard to see on this, but you see the black lines on those? Those are what we call basement lineaments. These are cracks, zones of weakness in the crust. And we can also image those with aeromag. 100% of all of these helium discoveries lay on these basement lineaments. That's where they occur. And the majority of them, 85% of them, actually lie on where the basement is high, so a basement closure structure. And like I said, aeromag, I can also see where I have magmatic bodies or old magmatic bodies in the crust. And that's what these red dots are. And these lines are dikes and sills that we see either at the surface or in the subsurface. So we can see hundreds of these things over this area that most of them are in the subsurface. There's Shiprock right there. That one's Shiprock. So that's on the surface. And you can see the walls, the dikes coming off it. I can see it. But look at all the other ones around that you don't see. Some of them on the surface, most of them in the subsurface. This is what these magmatic bodies look like in the subsurface. They can come in all different types and varieties and flavors, sills and dikes and stocks and laccoliths. So they come in all different geometric types. And remember I said when these bodies are rising, they create fractures. They open up existing fractures and they create new ones. And so just like when Shiprock, when it came up, remember you saw those dikes radiating off it? Well, there's the radiating dikes right there. That's what it's showing you. This has all been, experimentally proven when one of these bodies is rising up, what kind of fracture patterns. You get these radial fractures, and then you get these ring fractures that develop. And that's where the helium's coming up. So that's what you want to look around. You want to identify where those things are, because then that's where I'm going to start looking for helium. Okay? So, sure enough, I just showed you where all those magmatic bodies were. So now I overlay where all the helium, with known helium in the area. Where's it been found? 100% of all the known helium in this area, in the four corners, is within a half a mile of one of those intrusive bodies. That's because those intrusive bodies created the fractures and opened up the fractures, and the helium came up and they got caught in some trap nearby. So that's a great place to look. So now if I see these guys underneath, that'd be a great place to start looking around, right? It's within a half a mile of one of those things. So when I look around this area in the Navajo, this is all in the Navajo Nation. So this is Arizona, this is New Mexico. Our survey was all done mostly in northwestern New Mexico, a little bit in northeastern Arizona. We found 253 untested of these type of anomalies in the area. So there's a lot of prospectivity that we see just in this. That's only a small fragment of the Navajo Nation. And I've got a little bit of facts here. Of those, 35 of them had previously been drilled, of which 10 of them were producing helium wells, and 16 were producing helium wells. 10 of them tested helium but were not ever produced for whatever reason. And then 9 of them were just dry holes. So, I mean, that's a pretty good success rate. Even if I take the 16, that's 45% success rate, just going out here drilling around these intrusive, where there's no intrusive bodies on. The other technique we use is soil gas sampling. Bill mentioned it earlier in this first talk, where we talked about doing soil gas, helium soil gas. So here's basically a tool. Some of y'all may have seen us around doing this. You basically take an auger down, and then what you do is you draw a little bit of gas that's trapped in the soil, and then that gas is tested for its, using a mass spectrometer, does it have helium content. Now these are only drilled down about 2 to 3 feet in the ground. That's all we need to do. And they're just drilled down in the soil, and then we test the gases that are trapped within the soil to look for, is there anomalous helium that's trapped? Here's some of the areas we tested. We tested a lot. So this big red box was the area we did that Aeromag survey that I just showed you. That's the same area. So we did a lot of sampling in there. And we actually collected and sampled over 2,200 samples. So we did a massive amount of this. So we also have to determine what's background of helium. Remember, Stuart said there was 5 ppm on average, which is true. The average, global average, is 4.24 ppm of helium in the air. But it varies where you are in the world. So we collect a lot of air samples to establish what is the local background air, because that is what you got to determine what is true background. So in this area, it was actually 5.33 ppm, which I'm not surprised because there's a lot of helium in this area, so it's probably a little bit higher here. So what you do is then, here's your baseline, and where you see it start to inflect here, that's anomalous. That's telling me that those are anomalous helium readings. So here's an area where we talked about, we did a lot of testing at the Texaco Z well. Bill talked about that earlier, because it was a good place to test. Can this technique see a helium accumulation at depth? So we did a lot of sampling around it. Here's where the Z well is. And that had a little over 6% helium at 6,500 feet of depth. What's colored in here is, and these are in parts per billion above background. So if it's colored, it's anomalous. So we saw things as higher than as much as over 500 parts per billion above background associated with the Z well. And the contours are the seismic structure. So this is the structure of the Leadville reservoir. This is where the Z well is producing from. So you can see how it kind of conforms the anomaly to the structure. Not only that, here's the Z well. Those blue dots, that's an intrusive body at depth. Okay, remember I said there's intrusive bodies? Well, look there you go, right there, bingo. It's right underneath the structure. And the green areas are where I have intersections of fractures, basement lineaments and other fractures are the green areas. So remember, I have all the components. So perfect fit. I have a nice structure at the reservoir level, and I have intrusive bodies and cracks. So the last thing I'm going to mention is seismic activity, and you may have seen some of this. We do need this to determine the other aspect. The aeromag tells us where the cracks are, where the intrusive bodies are. The soil sampling tells us, well, there's appears to be an anomalous helium occurrence at this location, but it doesn't tell me where. I don't know where it is, okay? Seismic tells me where the trap is. Now I know exactly where to drill a well, okay? So I can then tell John where to put the X on the map, saying, this is where you need to put a well, because here's where the structure is. So this is over the Z well, and this is old seismic, sorry about that. Seismic looks better now, but this is over the Z well, so I wanted to show it. There's the Z structure, there's where the Z well is drilled. So this is, at this level right here is where the reservoir is, the lead well, okay? So you can see in this one dimension, you can see how you've got a little closure, a little trap in there. So with that, I'll just finish it off with, this is our exploration process that we use to find helium on Navajo lands or anywhere else. We go through with, I'd say, increasingly detailed aeromagnetic surveys. We then determine, from our aeromagnetic work, we then determine what areas to do soil surveys over. And the great ones would be where I have these intrusive bodies. Then we conduct seismic, and then we go ahead with initial exploratory testing. So that was it. Hey, do you want to run that video real quick? I think he's back up there, so there's the one up above it. There you go. There it is. That is, you're looking in real time of helium or alpha particles, which are helium, being thrown off a piece of metallic that's pure uranium-238. So you can actually watch it in real time. Anyway, it's pretty cool, huh? Anyway, that's good. You can turn it off. Any questions? Yes, sir.
Mr. You say that a lot of the inert gas is pretty much in the zones of where there was lava rocks. So whatever's above the ground, is there a significant amount of helium in those lava rocks that's above on the surface now?
Well, the helium is not really in the lava rocks themselves.
I mean, in it.
Yeah.
In the rocks.
Yeah, the helium's not in the lava rock themselves. What the lava rocks do is they open up the cracks and they heat up this rock. This is the rock, the helium. So those lava rocks heat this up above its closure temperature, and then they create the cracks that gas can then move out when it's rising up. So that's right. Yes, sir.
So your process for extracting helium, do you have to use vacuum to get it out? Is that one of the process?
No, that has to do with the fracturing I'm occurring is talking about what the lava, that's what the earth is doing. Okay? I'm not talking about man's, fracking all is dependent on what the reservoir is containing. So most of the reservoir is in limestone, which is called the Leadville limestone, which is generally very porous. So you generally just produce it out. There's no need to frack. Frack is very, very
In the process of extracting the helium, what chemicals are used to put in the water to extract the helium?
Well, I'll let John go into that. I mean, there's not really, I mean, you're talking about like drilling or things like that?
Yeah.
I'm gonna let John, he's gonna cover that,
Oh,
the
okay.
drilling part. I'm just telling you about how it
How it
gets
forms,
trapped in
yeah.
the subsurface.
Okay.
Is all, okay?
Oh, and then at what depth did you say that helium is located?
Oh, it is found as shallow as 500 feet. And generally around here, I haven't seen it any deeper than about 8,000 feet in depth. Where I've seen a helium, I would say a high percentage of helium, what I call a helium deposit.
That would be about roughly 5 miles into the earth?
No. 8,000 feet would be 1.5 miles
Oh, okay.
into the earth. Yeah. Okay.
Okay.
Oh, wait.
Yeah, one more. My name is Joseph Hernandez. I'm a student in that college. Where else throughout North America are there helium pockets? And are there other locations of this percentage? Because I think I attended meetings where they said that this is the only location that is rich, and that's why we're being targeted. But I'm sure there's more locations in the world, not just North America. And I believe, I read something about even Russia had a large deposit.
Yeah, good question. I'll first talk about what here in North America. One is, Navajo Nation is quite blessed with very high helium reserves. And there is a reason for it, because if you look kind of central, it runs along the New Mexico-Arizona border, is what's called the Defiance Uplift. So, it's called the Chusca Mountains and all that, but it's a large uplift, and it's also the Zuni uplift, is they're very old basement uplifts that you end up with granite rocks like this that were shallow, and they were in place very shallow about 1.7 to 1.9 billion years ago. So remember I said time makes helium to generate this rock. So over the Defiance Uplift in Zoom, they were old and they stayed shallow, which means they stayed at a temperature lower than their closure temperature for almost 2 billion years, which means helium would build up in this rock for a very long time. Then you had a lot of the volcanic activity starting about 30 million years ago, and actually even in around us up until the last million years, you had volcanic activity. So you had heating events that are heating this rock and releasing helium. So that's why the Navajo Nation is very unique. If you have a very rich, and it's because of these unique geologic factors. Are we the only place in North America? Absolutely not. There are some very rich places along in southeastern Colorado and the Los Alamos Arch. There are very rich areas in Texas, Oklahoma, Panhandle area, which is near the Wichita Mountains, also very high in helium. And there's people now looking elsewhere, so looking in Canada, places like that. So anyway, we're not the only place, but we are unique. These circumstances which create this are not everywhere in the world, and they're not everywhere in the United States. Okay, so they create rich places. As far as Russia goes, or Qatar, any of those places, they produce it as a byproduct of natural gas. But that gas has 0.02% helium. It is not rich. The stuff around here is 5 to 10% helium. They're 0.02%, which under the most circumstances isn't commercial. only reason Russia and Qatar develop it, because they have giant gas reserves that they're liquefying for LNG. And because they're already liquefying it, they're able to extract. And it's such a large amount, they are extracting this 0.02% helium out. But they're not rich.